Well, welcome, AP Chemistry people. This is Mr. Bergmann here, and I'm going to chat with you your first review podcast. We want to talk about the concepts of Kc, Kp, and Ksp. So let's kind of just have a general discussion. You're probably going to want to just take these in your notes, in your notebook, some kind of a review notebook, and then the other podcasts will kind of follow along. So let's just talk about equilibrium in general. And by the way, this is actually, this podcast will cover chapters 13 and then portions of chapter 15 in your textbook. Now, just the key things you've got to understand about equilibrium as we talk ourselves through this. Of course, this, by definition, the equilibrium by definition is when the rate of the forward is equal to the rate of the reverse reaction. So that should be a quick review. This is where we have reactions that have the double arrow. If you've got A and turns into B plus C or something like that, then you have A breaking apart into B and C going to the right, and to the left. B and C are reacting to get together. You can have both a chemical equilibrium, where these are chemicals, but you also can have a phase equilibrium. So for example, you can have water liquid, double arrow, water gas. And then you can say plus energy here. This would just be the boiling or the vaporization of water. And of course, you can go this direction and boil or vaporize the water, and you can go this way and you can condense the water, and it's related to temperature. Now, these questions, when you see them on the AP exam, they can appear kind of as mathematical or conceptual. When they're conceptual, they always follow along with the Le Chatelier's principle. We'll call it the Le Chatelier principle, because he's from France. Is that a French accent? I don't know. But Le Chatelier, and of course he said that if you apply a stress to a system at equilibrium, it will shift to relieve that stress. The stressors, if you recall, were pressure, temperature, moles. I think that's it. I have to think about that for a minute. I think it's just pressure, temperature, and or moles or concentration. And if you remember, if you're watching this in AP land, you have no idea what I'm talking about. But if you remember how to, never mind, no, that doesn't apply. I was thinking about date for the problem, but that's kinetics. So if we've got a system at stress, so you understand if I've got a reaction A plus a B turns into C. Let's say that this is plus some energy term. So this is an exothermic reaction. If you were to increase the temperature, what would happen to this equilibrium? Yeah, of course, if you increase the temperature, the energy is right on this side, it'll shift to the left, so you'll make more reactants. Right? And if I were to say add some A, of course, here's A, it's going to shift away from that, and that'll shift to the right, and you'll make more products. So this should be relatively simple. Now, how about if I take away C? And of course, if you take away C, that means move it away. That will shift also to the right. It'll make more products. Now, I want to talk about this take away. This is a little tricky. When they say that they take something away, they really can't just take a chemical away. They have to find something to react it with. So, for example, if I have a reaction that produces like an acid-base reaction, so let's say I have HC2H3O2, and that, of course, dissociates into hydrogens and acetates. That's an equilibrium reaction. Then what happens is if I add hydroxide to that, like sodium hydroxide or something like that, what you are essentially doing is the hydrogen reacts with the hydroxide to make water, and that shifts the reaction to the right. So when you're taking something away, you take it away that way, okay? So those are some conceptual things about Kc, or about equilibrium. Well, we should talk about like pressure. Pressure, what if I change the pressure? So I've got A plus B turns into C. And let's say these are all gases. All right. And if I were to increase the pressure, it shifts to the side with the least number of gases. So if you increase pressure, you go to the least moles of gas. So in this case, since I have 2 moles of gas on the left side, and the right side I have 1 mole, this reaction would shift to the right. Now, if I have a reaction A plus B makes C plus D, and so you have 2 moles and 2 moles, assume that all these chemicals here are gases. If you increase the pressure, there will be no effect. Also, there's another tricky question you sometimes see in the AP test. If you add a inert gas, then that will have no effect. Okay, so just kind of play around with that. I think you will. This is a relatively easy set of questions when you get to that thing. Now we can also talk about the constant. What's the equilibrium constant? Remember, that's big K. There's be a Kc and there's a Kp, if you recall. So Kc is the concentration K. So if I've got a reaction A plus B turns into C, and let's say they're all gases for the sake of argument here, and let's say that we've got 2C. Yeah, let's do that. So then the Kc would be equal to the concentration of C squared over the concentration of A to the times the concentration of B to the first power. Now the Kp, we write it a little bit different, but kind of the same ballgame. You'd say the partial pressure of C squared over the partial pressure of A times the partial pressure of B. By the way, A and B, of course, are both to the first power because, of course, there's a 1 in front of the A and the B there, right? Okay, so that's that. And then, of course, you begin at that point doing mathematical equations. Oh, before we do that, there is one important little equation. Now, this will be given on the AP test, but make yourself aware of it. It relates Kc and Kp. And that is Kp is equal to Kc times RT to the delta N. Now, the delta N is the moles. So delta N is the change in moles. So it's going to be, let's get this mixed up, so let me think this through here. So if I have a reaction like 2NO plus Cl2, and these are all gases now, goes to 2NOCl, and that's a gas. There are 3 moles of gas on this side and 2 moles, and so you actually just take 3 minus 2, that's a -1. So N would be equal to -1 for this particular reaction. Now, by the way, if it's 2 moles and 2 moles and N equals 0, then Kp at that point is equal to Kc. Okay? So hopefully that helps you with the whole Kc, Kp thing. And then we can just do some sample problems. I'll do one problem with you here. This is off of the 1988 test. So this is a real question off the 88 test from 1988. So we have an elevated temperatures. We have this chemical SbCl5. It's a gas, and it decomposes into this SbCl. It gets the reaction right here. So you may want to, it might be helpful is actually to print this screen and the subsequent ones, because I'm going to kind of be jumping back and forth, and I'm going to solve them on blank sheets of paper, and it'd be good to kind of have this in a book or something for you as you're doing it. Okay. So I'm going to rewrite this reaction. So we've got SbCl5, and that turns into SbCl3 plus Cl2. So we have a 1-to-1-to-1 ratio. Let me flip back here. We have 89.7 grams of SbCl5, 89.7 grams. I'm just kind of flipping back. I don't have a piece of paper with it in front of me. Is an evacuated 15-liter container at 82 degrees Celsius. So I have a container. Let's consider it a flask. It doesn't say. But this has a volume of 15 liters, and it's at 182 degrees Celsius. So that's what I know. What are they going to ask me to solve for? What is the concentration of the SbCl5 before decomposition occurs? So they just want, in question A there, what is the concentration? So concentration, of course, is the molarity, right? So I'm going to take 89.7 grams of SbCl5 in 15 liters. I then get the calculator out. I have to find the molar mass of SbCl5. Sb is 122, it looks like. 122 plus chlorine is 35.5 times 5. Molar mass is 299. So this is 299.5 grams in 1 mole. The grams will cancel, and I will get the molarity. So 89.7 divided by 15 divided by 299.5 on my calculator, I get a 0.1996. I think we could probably safely say 0.20 molar. So we have a 0.2 molar solution of SbCl5. That's question A, and that's pretty easy, isn't it? Question B said, what is the pressure in the container before any decomposition occurs? So they're not asking for a pressure. Okay, so when I ask for a pressure, we can do that. So the pressure question, well, it's just a PV equals nRT. This, though it's an equilibrium question, I haven't done an equilibrium problem yet. All right, I want to find the pressure, but I don't know the pressure. So P times 15 liters, right, is equal to the number of moles, which we've not calculated, have we? The moles I have would be 89.7 divided by 299.5. So 89.7 divided by 299.5. There's another way to do this. And that's going to be 0.299 moles times, and R is, of course, 0.0821. And the temperature, we have 182 degrees Celsius. I'm going to add that to 273 here on my calculator, and I get 455 Kelvin. So I'll take 0.299 times 0.0821 times 455, divide by the 15-liter container, and I get the pressure to be 0.745 atmospheres. Okay, well, we didn't have a question at all there that related to this. Okay, if the SbCl5 is 29.2% decomposed when the equilibrium is established at 182 degrees Celsius, calculate the value of either Kp or Kc. All right, so I have my reaction. SbCl5 makes SbCl3 plus Cl2. Now my molarity was 0.200, and this is going to be an ice table. We have no SbCl3 or Cl2. When they gave us this 29.2, they're essentially calculating X for us. They're telling us X is going to be. We're not going to say minus X here. This is going to diminish by some, but it's going to be 29.2% of 0.2. So if I take 0.292, that's 29.2 written as a percentage, times 0.2, I'm doing the Kc, of course, 0.292 times 0.2 gives me 0.0584. So this is 0.0584. That means, of course, since this is a 1 right here, this is plus 0.0584, and so plus 0.0584. Of course, this is 0.0584. Lordy mercy, 0.0584, and of course, 0.2 minus 0.0584 gives me 0.142. Now, these are, of course, the ending values, and of course, the value of the Kc will be the concentration of the SbCl3 times the concentration of the chlorine gas over the concentration of the SbCl5. And of course, I just simply plug in the numbers that I have here. It's 0.0584 times 0.0584 divided by 0.142. Get my calculator out, 0.0584, which essentially square that, divided by 0.142 gives me 0.024. Now, a mistake I have seen students do before when they say that it is a particular amount decomposed, I'm going back to this particular screen, is that they don't realize that these are going to be the same number. They'll say this is 0.0584, and they forget that this also is that number. And if this was a 2, by the way, of course, this wouldn't be 0.0584. This will be twice that amount. It isn't, so that's not the problem. But I wanted to kind of make that clear to you as we're solving that. All right, let's look at the next portion. In order to produce some SbCl5, a 1 mole sample of this is placed in a 2-liter container, maintained at a different temperature from 182. All right, by the way, when you change, I don't think I said this earlier, but the only way to change the value of the K is to change the temperature. So since we're at a different temperature, our new K is this number. How many moles of chlorine must be added to produce the number of moles in a 0.7 mole? All right, we got it's a bunch of math. Okay, so let's get ourselves a blank screen, and let's write our equation now. SbCl5 makes SbCl3 plus chlorine gas. Now, we got to put a bunch of numbers in here. Now, I have a 1 mole sample. Now, wait a second. It's placed in a 2-liter container. All right. So the concentration of the SbCl3 will be 1 mole over 2 liters. So So that's going to be a 0.5 molar solution. I want to work in molarities. So the SbCl3. So this, so do an isotable. This number here is 0.5 molar. Got it? That's the first thing I know. I also know Kc is 0.117, so I'm going to write that down. Kc is 0.117. All right, at this temperature, how many moles of chlorine must be added to this container to reduce the number of moles of SbCl3 to 0.7 moles? So we're trying to find the moles of chlorine. We're going to call this X. And we want to get this ending concentration to be 0.7. So the reaction, by the way, as a note, is going to shift because there is 0 SbCl5, so it's going to need to shift to the left. So this number is going to become a minus number. Now, they asked this in a very weird way, I think, but oh well. They want it to be 0.7 moles, but in terms of molarity, divide that by 2. That'll be 0.35 molar. So we want to end up with a 0.35 molar. Oops, not that. This will be 0.35. So of course, this number, I can do that in my head. That's 0.15. And this will be minus 0.15, or X minus 0.15. Over here, this one, of course, on the left side over here, the reactant side, this will need to increase by, because of the ratio, 0.15. 0.15. And so now we know that Kc, which is 0.117, will be equal to the products, which will be 0.35 times X minus 0.15 divided by 0.15. I'm going to now get my solver out. And so on my calculator, let me clear my calculator here. Math 0. How am I going to type this into my calculator? I don't know how I'm going to do this. I'm just think about it here. I will just take, well, I'll just take this term here minus this term. So I'm going to take 0.1177, there we go, minus parentheses 0.35 parentheses X minus 0.15 parentheses divide by 0.15. So let me do that. 0.117 minus parentheses 0.35. It would be good if you have your calculator out, and then you can do this yourself. I'm typing this into my calculator right now. And now the X, if you think about it, has to be a number bigger than 0.15, right? Because you can't have a negative value. So I'm going to say like 0.4, I don't know, for my guess. Do the alpha solve thing, and I get 0.317. That's not too bad. 0.317. Now that's the molarity. So let me do this here. The question wasn't the molarity, but the moles. So X is 0.317 moles per liter times 2 liters over 1. The liters cancel. So the number is going to be 2 times 0.317, or 0.634 moles. Okay? So, you know, we didn't use the KCKP equation. This just happens to be the question they asked in 88. You can do lots of different questions. And so you need to kind of prepare yourself for all. You'll do a bunch of them in class. And so I don't want to spend too much time doing that. Now, there's sort of a second portion of this whole equilibrium conversation that we should certainly have, and that is the concept of the KSP. KSP is the solubility product. And this is measuring, this is now in chapter 15, by the way, so we kind of skipped chapters in your textbook. And this is sort of the end of chapter 15. So I'm not doing it in the order that we necessarily taught it. And of course, this relates to ionic compounds that are insoluble. This is kind of a weird deal. It is the solubility of insoluble compounds, or the small solubilities. These are very small numbers. So for example, if I have a chemical like Ag2CrO4, which is a solid, and which is, we memorized from a Nakel-Noso rules, is not soluble, but it is slightly soluble. So you would get turned into 2 silver ions plus CrO4 2 minus. And since this is a solid, and this is a Q, and this is a Q, the KSP, we ignore the solids. So it's just going to be the concentration of the silver squared times the concentration of the chromate right? And then we can solve these questions. This is where, if you recall, we used the S, right? Instead of using X's, we used S's because S stood for the solubility. And so S is the molarity that will dissolve, and the KSP is the number. So oftentimes you'd either solve for the KSP given S, or you would solve for S given the KSP. So there's two ways to solve these particular problems. They are inherently mathematical. So that's an important, I'm going to kind of discuss this conceptually for a few moments before we do a single problem. But another thing that's important to understand is that oftentimes you will have a mixture of compounds, of chemicals. For example, I could say you have Ag, so many grams, I don't know, 10 grams or something, of the Ag2CrO4. And you're mixing it with, say, some sodium chromate, Na2CrO4. And then, 2 grams of this. And what I oftentimes see students do is they'll write this reaction, Ag2CrO4 plus Na2CrO4. And you should never, ever, never, ever, ever, ever do that. When you have a KSP problem, you write the equation that I wrote earlier. You would write this equation right here. I'll highlight it in green. This is the equation, and if you have so many grams of a particular amount of this, and you have this, you just will find the molarity of this, and that's going to give you a number. What you essentially have in the fancy term is that you have a common ion. Okay, so in this example here that I'm talking about, if I added some sodium chromate to it, 2 grams of it or whatever it might be, you would find the molarity of that, and then you would plug that into your chromate in this expression right here. Do not react them together, but you write the main KSP reaction. That is the key to these. Oh my folks, if you get this, that will so improve your points if we get a question on KSP on the exam, which we certainly might. And very, 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 very important. Also, there's this notion of does a precipitate form. Oftentimes, they'll ask, does a precipitate form? So if I've got, again, my example, the silver chromate, Ag2CrO4, makes the 2 Ags plus the chromate. What you would do, of course, is you would find the QSP and compare to the KSP. Turns out the KSP, I have the table. If you recall, there was a big table of KSPs. It's found in the back of your textbook. In the blue book, the one I'm looking at for Mr. Bergmann's class, it's on page 752. It's also in the back. But the silver chromate KSP actually, numerically, at 25 degrees Celsius is 9 times 10 to the minus 12th. And so if I wanted to see if a precipitate would form, if I knew the concentration of the silver and the concentration of the chromate, let's say this is 3 times 10 to the minus 3rd, and this is 2 times 10 to the minus 5th. I don't know. You would multiply these, squaring this, of course, right? You would take, just solve for it, and if it was bigger, if the KSP is bigger than the QSP, then there is, actually I like to do it the other way. If the QSP is greater than the KSP, then yes, you get a precipitate. And if the reverse is true, the answer, of course, is no. So this is, again, going to be an example of opportunities where you probably want to look at a bunch of examples. Now, I have an example that you don't have in your packet from 1994. So I was teaching AP Chemistry at this time. Isn't that sick? Okay, no, I was not teaching it in 1994. Was I? No. I started teaching in 1991, like you care. Okay, I started teaching AP a few years later. All right, so here's a particular, you may want to print these out. There's actually 4 screens I have of the question. It goes A, B, C, D, or whatever, right? So here's question A. We have magnesium fluoride. In a saturated solution of magnesium fluoride at 18 degrees Celsius, the concentration of the magnesium is this number. The equilibrium of the equation. Write the expression for the solubility. Oh, this is such an easy question. The KSP, here's our reaction, is going to be equal to the concentration of the magnesium times the concentration of the fluoride squared. It is an easy, easy question. This is very true of AP test questions. Question A is almost always like just a softball question, as I like to call it. So bloomin' easy. Don't overthink question A. Now, question C or D could be kind of rough, but let's do them one at a time. All right, listen to question B. It says to calculate the equilibrium concentration of the magnesium in 1 liter of saturated magnesium fluoride in which 0.1 moles of solid KF. Now, this is where you've got MgF2 and KF. And do we write them together? No, and no. We write MgF2 goes to Mg2 positive plus 2 fluorides. Now, what do I know about this? I have a 1 liter of saturated MgF2 in which 0.1 moles. Basically, they've given me the KF. KF, of course, completely is in Nakelnoso, completely dissociates into potassiums and fluorides. And the chemical that I care about is the fluoride. And they've told me that this is 0.1, right? You know what they didn't do? I think I maybe skipped a portion of this question. Hold on. And then, of course, then you're going to ask you to solve for S. And so I'll set this up and we'll come back to it because we need to solve for something else. Maybe I didn't read the whole first question. And then you'll say the KSP would be equal to S times 0.10 squared. And if we know the value of the KSP, we can solve for S. I'm thinking they maybe asked us to solve that and calculate its value. Okay, I'm just a ditzoid. Okay, so when this breaks apart, let's go back to part A. This is an S, and this is a 2S. So we can say this is equal to S times the quantity 2S squared. Now, it's very, very important that you understand that this is 4S cubed. This 2 right here is also squared. And they gave you this 1.21. This equals S. It's the solubility, or the molar solubility. So I'm going to simply take 4S cubed. So I'm going to take 4 times 1.21 e negative 3 and cube it. So let me get my calculator here. So I'm going to take 1.21 e negative 3. I got to cube it, right? Caret cubed times that then by 4. My KSP is 7.08 times 10 to the minus 9th. So now I'm going to use that here, of course. 7.08 times 10 to the minus 9th is equal to S times 0.1 squared. So I just take the 7.08 e negative 9 divided by 0.1 squared. And I get S to be 7.08 times 10 to the minus 7th. And that's the concentration of the magnesium, isn't it? And that's the answer to part B. Now, here's part C. Now, you may want to copy it down. You may want to just print the screen. You can print screens on podcasts if you're watching it at least on a computer. Predict whether the magnesium precipitate will form. Okay, this is that will it precipitate form. All right, now again, I see oftentimes students writing out these reactions. You essentially are just going to do MgF2 goes to Mg2 positive plus 2 fluorides. Do not write the reaction. This is just giving me the magnesium concentration and the fluoride concentration. So I have a 3 times 10 to the minus 3rd molar magnesium. This just gives me the magnesium because all nitrates are soluble, right? So the concentration of this is 3.0 times 10 to the minus 3rd. And the fluoride is 2.0 times 10 to the minus 3rd. So we're going to solve for the QSP, which is just the KSP with the numbers that they give you. So that would be 3 times 10 to the minus 3rd times 2.0 times 10 to the minus 3rd. Now you've got to square that. Don't forget you got a 2 there. So I'm going to get my calculator. 3e negative 3 times 2e negative 3 squared. And I get 1.2 times 10 to the minus 8. That's the QSP. Now the KSP, I've lost it now. You've got it written down. I have to jump back. Was 7.08 times 10 to the minus 9th. That's the KSP. And this is a bigger number than this, 10 to the minus 8th, of course. So QSP is greater than KSP. So yes, a precipitate will form. Okay? You have to prove it, though, with math. All right. At 27 degrees Celsius. Now note, different temperature, I believe, because one of the other ones at 18 degrees. Yes, it was. So this is going to have a different KSP. Okay. The concentration of the magnesium in a saturated solution is this number at 27. Is this exothermic or endothermic? Explain. Okay, so you've got this reaction, MgF2. You're getting tired of me writing this, aren't you? But that's how you do it. We want to ask this question. Now, at 18 degrees Celsius, now we have to go back to part A. At 18 degrees, this S was 1.21 times 10 to the minus third equals S. At 28 degrees, it's 1.17 times 10 to the minus third. That's the molar solubility. So when you increase the temperature, 1.17 is smaller than 1.21, right? So this is smaller. So at higher temperatures, it becomes less soluble. You just sort of think this through. We're basically saying, which side are we going to put energy, on this side or on this side, right? So when you have a high, this is 1.21 at a low temperature. And so when it becomes smaller, it has to shift to the left, doesn't it? This is really a conceptual question. It's not even mathematical. This was 1.21, but it's going to shift to the left at a higher temperature because it went down. So the energy, you're increasing the temperature. The energy has to be on this side, doesn't it? Because the reaction is going to shift to the light, so to the left. So how would I answer this? I would say, first of all, of course, that it is, since energy is on the right side, it is an, let me put a different color. It is exothermic. And I would say because, that's the abbreviation for because, as you increase temperature, the solubility of magnesium fluoride goes down, which shifts the equilibrium to the left. And I might show, I would show this reaction right here. Whenever you're answering something that's conceptual, please, please, please be verbose. Say all the things that you think are appropriate. And if yeah, and I'll talk about that as we progress. Okay? That's our quick, brief. I don't know if that was that quick. It was 30 minutes. Podcast on KC, KP, KSP. We'll do problems in class. We'll talk to you. Bye.